All right, well, welcome back for the final seminar of today for CALE, or the Cloud and Container Apprentice Linux Engineer Program. This is the last today, but not the last for the rest of the week. We're still doing software-defined networking tomorrow morning and Cloud Foundry, but for now we're going to, of course, talk about Kubernetes, the last of our container-based talks, and Ihor's going to do the talk today. And if you have questions, since we are recording these sessions, please put up your hand and I will come and bring you the microphone. If you don't have the microphone, we're going to have to get the question repeated before we go on.
So welcome everyone. My name is Ihor Dvoretskyi. I'm a developer advocate at Cloud Native Computing Foundation, and I'm also one of the contributors to Kubernetes project, and I actually started contributing to Kubernetes around 3 years ago, even before I joined CNCF full time. So today I'll make the brief intro to Kubernetes as a technical project. So many people are using Kubernetes today. At the same time, so many people are interested in how to get started with Kubernetes. What are the basic concepts of Kubernetes? How can you use it from the really basic level? And also, at the final end, I'll make a brief intro into the Kubernetes community. How can you dive into Kubernetes, not as an operator that is using Kubernetes, but as a person who'd like to contribute something there. Before we'll start, I'd like to count your hands. How many people here in the audience already have experience with Kubernetes? Fantastic. So this presentation is exactly for those people who don't really have experience with Kubernetes. Right, so another disclaimer and some kind of announcement that this presentation and today's workshop, it's pretty short and pretty brief. All the information that you will hear and see at this workshop today is based on the Linux Foundation course, LFS 158X, that is available on edX, the open platform. It's available for free. You can also able to purchase an additional certificate there. But again, the course outline is available for free. You can repeat all the stuff that you will hear today there online after our session, so please do it. And actually, if you have already passed this course on edX, you'll also notice a few well-known things for you. So please check it on edX. So let's start from the basics. Let's start from why do we use Kubernetes? What is the purpose of Kubernetes? And why do we need containers, first of all? Because as you probably know, Kubernetes is a container-related technology. So what are containers? Any people here that are familiar with containers at all, not only with Kubernetes? That's really good. Much more people. So that's really well-known content for you. So containers is the lightweight technology that allows you to bundle and package some pieces of your code, some libraries into some isolated space that's typically called container, right? And it can be run on almost any kind of environment that supports this technology. So the most well-known technology, the containerized container technology today is Docker, but it's not the single technology that exists in the world. So you probably have had experience or have heard about OpenVZ containers or LXC containers. And Docker containers, of course, they are kind of different. So if we'll compare Docker with LXC containers, they have a bit different goals. They are using approximately the same technologies on the basic Linux level. They're using namespaces and C groups in Linux kernel. But LXC was designed, first of all, as an alternative to the typical big virtual machines. We had right here in this room yesterday, we had a workshop about virtual machines and KVM and libvirt. If you had a chance to attend it, that's great. So you could hear some basics about the virtual machines, how they're different from their real bare metal machines. LXC containers are different from the technology perspective from the virtual machines, but they are not offering so huge level of isolation. You are not able to run, for example, Windows on LXC containers, but they provide you almost the same experience from the user perspective. If you're using LXC containers, you still use almost the same big operating system as you use with virtual machines. With Docker containers and similar technologies like Docker, there is a different approach from the end user perspective. Docker was designed not to emulate the big virtual machine on the bare metal machine. Docker was designed specifically for applications. Docker was designed for the application developer and application consumers. Docker is intended to package an application, to bundle some pieces of code, bundle some libraries into one box that could be easily shipped from one machine to another, that could be uploaded to some remote storage, like Docker Hub, well known, and you could pull this box from a different machine and run the same piece of code on a different hardware or software. So that's the biggest difference. That's in brief about what are containers and how they have been designed and what's the difference between different types of containerized technologies. So why people select containers? Again, if you are able to choose, for example, virtual machines to secure environment, to isolate your environment, and to build some multi-tenant environment, why should you use containers instead of different technologies? First of all, containers are portable, so they are offering you exceptional level of portability. As I mentioned before, container can be imagined as a simple box with some code that could be easily shipped anywhere. You can easily, if you're speaking about, again, for example, about Docker containers, you can easily pull all the code from the Docker container, pack it into Tarball, and ship it even on their USB flash to a different machine. It's not the recommended way to ship contents of the containers, but it still works. Containers are immutable. So immutability in this case means that everything that happens within your container does not affect your host machine or doesn't affect any other machines. Containers can be easily updated. If we're speaking again about Docker containers, they have the layered structure where you have the base layer, for example, with pretty tiny Linux-based code base, like the small operating system style code base, like Ubuntu Core, for example, or Alpine Linux. On top, you may have some extra binaries that are layered above of that. And if you'd like to update your application that is bundled into a container, you don't need to rebuild your entire container. You simply need to update exactly that layer that contains some changes. And that's also really good for infrastructures and for environments where you don't need to spend your CPU time. You don't need to waste your network bandwidth to, again, download exactly the same what you already have in this container on your existing container. You simply can apply the incremental updates to your existing environments. Another benefit is that containers are prepackaged. So if you're using tools like Docker Hub or similar public or private container storage systems, you don't really need to build everything from scratch. For example, you'd like to run a container that contains Nginx. Nginx are already Nginx containers, and containers that contain Nginx are pre-installed, are already available on Docker Hub. You can easily pull it with one command, and with the second command, you can easily run it on your machine. You don't need to build everything from scratch on your machine. Again, you don't need to waste your personal time, your CPU time, your resources of your local machine. Containers are lightweight. They are much lightweighter than regular virtual machines. If you typically should wait approximately a few minutes, even on the most powerful hardware, to spin up the new virtual machine, spinning up the lightweight container can take you like a few seconds, because container contains only that code base that you require. It doesn't contain all the full operating system that you may have with the virtual machines. And containers are excellent for microservices, because with the microservices approach, where you have one microservice that acts as a front end for your application, another microservice that is acting as a backend for your application. You can also have some database that is a separate microservice, and so on and so on. So they are excellent for the model of microservices where you may rebuild your front-end application 10 times per day, but you don't touch your database for years. So you can simply rebuild your containers that contain the front-end code, not touching anything else in your environment, and it won't be affected by anything. And the final benefit of using containers, again, if you're speaking about Docker and similar ones, is that they can use the standard wrappers, again, as Docker Hub, as some private and public registries, for example, offered by Red Hat, Google, or something self-hosted. So on this application, on this slide, you may notice the architectural difference between containers and virtual machines. In the left part, you may see the virtual machine, and in the right part, we have container image. And you could notice how containers are much simpler than virtual machines. So here at virtual machine, we have the bare metal level, we have the host OS, exactly the same as we have with containers. But right here, we have a hypervisor which allows you to run the virtual machines, and it requires extra resources from your environment to run these virtual machines. You should also run the guest OS. If you'd like to run, for example, Ubuntu Linux, virtualized Ubuntu Linux on top of bare metal Ubuntu Linux, you have to virtualize entire Ubuntu Linux that can wait a few gigabytes, and it will consume some amount of RAM and CPU. And at the final end, we have applications in binaries. So what's the difference of the virtual machines with containers? We don't have the layer of hypervisor. We don't have the layer of guest OS. We don't need hypervisor because our host OS, sorry, not the host OS, but guest OS here. So in the case of containers, our host OS is exactly that layer where you can run your containers. Ability to run containers is bundled into Linux kernel, and containers are using the standard mechanisms of Linux kernel. They're using cgroups and namespaces just for isolation and providing some resources and probably restricting these applications of using some extra resources they don't require. We also don't need the guest OS because everything that we need for containers is already bundled into container itself, is already a part of our application. So this is the biggest difference between them. And it allows us to use much less resources for running containers compared to the virtual machines. There are some downsides of this, of using containers versus virtual machines. There are a lot of cases where you should use virtual machines, not containers, because virtual machines can provide you much more higher level of isolation. Virtual machine is totally isolated from anything on your machine. You can also run some different operating systems on top of virtual machines. For example, if you're running containers on Linux, your applications within your containers should be only Linux-based. But with virtual machine, you can run Windows, you can run BSD systems, and so on. So there are enough cases where you should use virtual machines, but there are enough cases where you should definitely start looking at using containers as an alternative to your virtual machines. Now let's speak about the container management systems. So coming back to Docker, coming back to the single container and single containers, it's pretty easy to run Docker and Docker container on a single machine, right? Just install Docker on your Ubuntu laptop, run a single container, and that's all. Everything works. You may have more issues if you would like to run containers on a higher scale. For example, you have not a single laptop, but you have a cluster of 10 machines, or you have an entire data center of 1,000 machines, or you have multiple data centers around the globe which contain 5,000 machines. And you still would like to run the same applications on all that 5,000 node cluster. So it could be really complicated with a pure Docker. So some technologies should exist in this era. If you don't want to use them, that means that you have to develop something on your own. But I definitely would not recommend you to do it, because other people already did it. So the most popular container management systems today are Kubernetes. That we'll speak more about it today. There is also Docker Swarm and Compose. Docker Swarm is actually the real alternative to Kubernetes. It allows you also to run containers in the multi-node environments, clusterize them, and so on. And there is also Mazes. I will not dive into details and difference and the major architectural difference between Kubernetes, Docker Swarm, and Mazes. I should only mention that Kubernetes is the flagship technology in this era today. And most of enterprises, most of companies that are considering using some container orchestration and container management system today, they prefer using Kubernetes. So Kubernetes. First of all, what is Kubernetes? It is an open source system for automated deployment, scaling, and management of containerized applications. Kubernetes was originally developed by Google. Google, if you don't know, everything that is being run at Google is being run in containers. If you are using some Google services like Google Maps or Gmail or, I don't know, Google Play on your Android phone, every application, every Google application that you open interacts with containers on the Google side. And the internal tool that Google is using for managing all these containers on their scale, it's extremely huge scale, is called Borg. And actually, Google started using containers approximately 15 or even 20 years ago, in the beginning of the previous decade. And they had huge experience of managing containers, and they collected a huge amount of best practices. What should you do as an operator with the containers? How your applications should look like to be run in the containerized environment, in the containerized environment, and so on. So in 2014, Google open sourced Kubernetes. The first commit to Kubernetes repo on GitHub appeared in June 2014, and until mid 2015, it was not production-ready version. It was more technology for not for everybody's production consumption, but to take a look what do we have in the container space today. At the middle of 2015, Kubernetes reached its first major milestone. Version 1.0 was released. And exactly at that time, Google decided to move Kubernetes outside of Google. And they donated this project to the Linux Foundation. And in a few months after that, the Cloud Native Computing Foundation was established. So Cloud Native Computing Foundation, we are one of the biggest projects under the Linux Foundation umbrella. Today, we have not only Kubernetes, we have more than 20 different projects, but they are all forming this whole ecosystem where Kubernetes is one of the most important projects. So what are the key features of Kubernetes, why people prefer using it instead of different technologies, or instead of its competitors, or instead of like using raw containers without any kind of automation and orchestration? So first of all, Kubernetes is self-healing. If you can properly set up, and it's not so complicated, if you will properly set up your Kubernetes cluster, and if you'll properly set up your applications on Kubernetes, you should not care about recovering something if something will be destroyed. That's again, we are coming back to the basis and the basic concepts of using microservices and using containers. The origin of containerized applications was, so original containerized applications were mostly intended to be used in the stateless environments, in the environments that don't require any state, where you can, for example, you may run an Nginx container that doesn't contain any data. It's not a database. It's just an Nginx. It's just a front end for your application. It could be easily destroyed at any moment of time, and it could be easily provisioned in the next few seconds. Another big benefit of using Kubernetes is that it allows horizontal scaling. So imagine if you are an owner of some online store, and you are selling some fruits, for example, or some mobile devices. So typically, your online store requires three machines that are deployed in some public cloud. That's fine for you. You can easily work with that scale, but next week the Black Friday happens, and the load on your cluster raises up a lot, because so many people would like to purchase your goods for the holidays. In the non-containerized environment, without Kubernetes or similar tools, you had to manually deploy extra machines and manually deploy your applications on that machines and connect them in some way. Kubernetes allows you, if the underlying infrastructure supports that, for example, like Google Cloud supports that, so you can easily add a few nodes to the existing Kubernetes cluster, and Kubernetes will schedule your application containers into that nodes. And after you'll reach the peak of the customers that are accessing your online store, it can be also scaled down. So you had 3 machines before the peak. Now you have back 3 machines. That will save some amount of money for you if you're using the public clouds, for example. Another benefit is the service discovery and load balancing. So again, you can, with Kubernetes, you have many applications deployed on multiple containers on your Kubernetes cluster. These machines may have only one entry point, and Kubernetes, like entry point from the outer world, but Kubernetes will handle everything else. Also, another benefit is that Kubernetes allows you to have the automated rollouts and rollbacks. So if you are releasing the version B of, you currently use version A of your application, you would like to release version B of your application, you can do it with Kubernetes with a few clicks, or with a few actions from Kubernetes itself, and with almost 0 downtime. The same with rollbacks. If you figured out that your application B is not working properly, and you'd like to roll back to version A of your application, you can also easily do it with Kubernetes. Also, Kubernetes allows you to store secrets and manage your configuration of your cluster, so you don't need to use anything external. Everything is bundled into Kubernetes. And also, it allows you to manage your storage, especially if you are using some public clouds that are natively compatible with Kubernetes. For example, GKE, which is a Google offering on top of that use vanilla Kubernetes, but on Google Cloud. So you can easily, from the single Kubernetes control plane, you can also manage storage. Let's move forward with the Kubernetes architecture. So on this slide, you may see the really high-level overview of the Kubernetes architecture. So just in brief, I'll dive into details later, but just in brief, so for those people who can probably not see it properly right now. So here we have a user, an end user, an operator who operates the Kubernetes environment, who would like to perform some actions here. He may access Kubernetes environment with CLI, with APIs, or using the web dashboard. Here we have the master node or control plane, which contains API, server, scheduler, and controller. And here we have worker nodes. Worker nodes are dead places of Kubernetes cluster where your actual workloads are being run. So your containers, if we are speaking about Kubernetes as a container management system, your containers are being run on the worker nodes. So what is the master node or control plane? So control plane is the brain of Kubernetes cluster. Every single operation that happens within a Kubernetes cluster happens because of the control plane. And here again, on the slide, on this diagram, you may notice that user that is accessing, that is interacting with the Kubernetes cluster is accessing it via CLI, APIs, or dashboard that are reaching out to API server. So API server is exactly that part of Kubernetes cluster, is that part of Kubernetes architecture that allows you to perform some actions. So you as an end user, you're reaching API server that will call another components of Kubernetes cluster. There is a scheduler on control plane that allows you to schedule your workloads in a proper way. There are also some different techniques how can you properly manage your applications on Kubernetes. For example, if you're using Kubernetes in a hybrid environment where you're using your own bare metal machines in your own data center, but you also would like to run some workloads on public cloud. So you have already invested some amount of money into your hardware, so you'd like to utilize your hardware first of all. Your public cloud machines can be used for some extra workloads when you are running out of resources on your bare metal cluster. But Kubernetes scheduler can allow you to provision your applications first of all on your bare metal, because your bare metal cluster should be utilized as first of all. But if you're running out of resources on your bare metal cluster, scheduler will provision also these applications on the public cloud. There is also the controller that actually controls what's happening within the Kubernetes cluster. On this slide, you can see that we have a single node, the single green brick. But for the real production environments, community is suggesting, we're usually suggesting to build an environment, to build the clusters with at least 3 master nodes with the purpose of HA. Worker nodes, as I mentioned before, is exactly that part of Kubernetes cluster where your applications are being run. So again, if you'll compare that with the human's body, if control plane is the brain, worker nodes are acting as hands or legs. So you are sending commands from your brain to your legs to go somewhere, for example. So the same happens with your Kubernetes cluster when control planes sends commands to worker node to perform some action. Worker nodes are exactly that machines where containers are being run and where you have your applications deployed. Sometimes worker nodes can be combined with the control plane, with the master node. So exactly the same machine, the same laptop, for example, can have a role of master node and a worker node. But this case can be only suggested for some development environments, only for evaluation purposes. If you'd like to take a look what's happening with what is Kubernetes, for example, and how can you use it, not running that on a huge amount of resources. But if you are considering deploying Kubernetes clusters for the real production, we can strongly suggest you to separate your master nodes, your master workloads from their worker nodes. So anything that could happen on the worker node will not affect your control plane and vice versa. Worker nodes, they have the following main components. So kubeproxy is the networking element that allows master node or control plane communicate with the worker nodes. Kubelet is actually a local agent on the worker node that accepts commands from the control plane to perform something. So kubelet is the local agent on a worker node that performs some action. For example, it provisions containers. There's also the container runtime on the worker nodes. Container runtimes are like the well-known ContainerD, which is a part of Docker project. Before ContainerD as a part of Docker project has appeared, container runtime could be called as Docker itself. Projects like Rocket or anything similar. So container runtime is exactly that piece of software, that part of software that provisions containers themselves. And also on this diagram, you can notice pods. So the big concept, like pod is actually the atomic unit, is an atomic concept of Kubernetes cluster of Kubernetes workloads. So if you are performing some action with Kubernetes to run some application, it will not directly run them in containers, but rather it will happen in pods. So pods is an atomic unit that contains a single or multiple containers. Here on this diagram, you can see how what is the process of interacting between kubelet, between CRI, the container runtime interface, and containers themselves. So we have kubelet, we have the CRI protobuf and CRI shim that are parts of the container runtime interface. There is a container runtime itself and containers. The reason why it's not explicitly mentioned here, for example, you don't see word Docker here, or ContainerD or Rocket, is that because at Kubernetes, we would like to save compatibility and provide a universal interface and provide a universal standard for different solutions that could be used on different Kubernetes clusters. So the early days and the early versions of Kubernetes have had Docker bundled into the core of Kubernetes, but not all the consumers and not all the users been satisfied with that, because using Docker has many benefits, but also many downsides. So if there is a different solution that exists in the market, you'd like to use it as an alternative to something different. So container runtime interface is exactly that piece of software that allows you to connect different runtimes to your Kubernetes cluster. But again, like today, ContainerD is probably the most popular and well-known container runtime interface that is being used with Kubernetes. So now let's speak about the Kubernetes configurations. As I mentioned before, you can deploy Kubernetes in multiple ways, Kubernetes clusters in multiple ways. The easiest way to deploy Kubernetes cluster is the all-in-one single node installation. It's pretty easy. It doesn't require so much time. It doesn't require so many physical resources. It doesn't require so many cloud computing resources. You simply run everything on the single machine. It's really good for the development purposes, for the evaluation purposes. Again, as I mentioned before, it's the best way. How can you take a look at what is Kubernetes or run some simple applications on top of it? But it's definitely not the production case for Kubernetes. Please do not ever use this configuration for your production clusters. Another kind of configuration is with the single node etcd. Actually, I haven't mentioned etcd before. So etcd is a key value store here on a control plane. etcd contains information. It stores the state of your Kubernetes cluster. When I mentioned before the benefits of using Kubernetes, I mentioned also one of the benefits is that you don't need to use some external store outside of your Kubernetes cluster to store the state. So etcd is exactly that component of Kubernetes that stores the state of your cluster. So coming back to configurations, you may use the single node etcd, the single key value store, the single master, and multi-worker installation. This case, again, we don't really recommend it for the real production use cases, but if you have some basic workloads, you can start with this. So you will have the single master. It will be the single point of failure for you if your master will die, your Kubernetes cluster will die. But you will have multiple worker nodes that could be placed in different data centers, for example, or in different regional zones in your public cloud. So if something will happen with one of your worker nodes, another worker nodes will continue working properly, and your applications won't be affected by any downtime if you have designed it in a right way, of course. I'm speaking about the design of application itself, not the Kubernetes cluster. The similar approach is having the single node etcd, but multi-master. Here you are moving to the high availability of your Kubernetes cluster, again with the multiple worker nodes. And the way how we really recommend you to deploy Kubernetes clusters for the real production use cases is to have everything multiplied. Here you should have multi-nodes etcd cluster. You should have multi-master control plane and multiple workers for your workloads. The way how can you install Kubernetes locally on your Linux machine, you may use a tool that is the official tool by Kubernetes community that is recommended by default by Kubernetes community for the local workloads. It's Minikube. Another really popular approach is to use Ubuntu and LXD. There are a bunch of scripts on Kubernetes. There are a bunch of recommendations on the Kubernetes documentation. How can you run Kubernetes on top of Ubuntu with LXD? Another way of running Kubernetes locally that is not mentioned on this slide, if you're using MacBook, you can use the latest versions of Docker to run Kubernetes. So support of Kubernetes for Docker was presented around a year ago at DockerCon in Europe, in Copenhagen. And since that time, Docker made a big job of making Kubernetes as a first-class citizen in their local Docker installation for MacBook. And as far as I remember, it's also available for Windows, but you require Hyper-V. But yeah, as I mentioned, Minikube is the preferred and recommended way to create the all-in-one Kubernetes setup is the recommended way of how can you easily spin up the simplest Kubernetes cluster just for evaluation purposes, just to look at Kubernetes, what is it, how can you run some applications on top of it, and emulate some of your practices that you will later use on your big multi-node and multi-worker environments. If we'll speak about the ways of how can you deploy Kubernetes not locally on your machine, First of all, you may use the on-premise installations using the on-premise VMs or on-premise bare metal machines. That's a typical approach of running some kind of software. The good thing about Kubernetes that is widely supported by almost all well-known and popular and widely adopted public cloud providers, including Google, of course, because Google, with Google Kubernetes Engine, was one of the pioneers in this space. Also, Azure offers AKS service, is the Azure Container Service, and Amazon offers EKS. It was announced not so much time ago. So all these ways are offerings by the major public clouds, public cloud providers. How can you spin up your Kubernetes cluster? Again, terribly easy, just in a few clicks and in a few seconds or minutes of your time. And of course, not all the solutions are mentioned here on this slide. That these are the most popular solutions by the most popular public clouds. There are also some self-managed solutions. How can you run Kubernetes on almost any kind of environment, but you have to manage it on your own? The most popular way of deploying Kubernetes anywhere on any kind of public or private cloud and any kind of environment is kubeadm. So kubeadm is de facto the community standard. How can you run Kubernetes? And actually, here on the Kubernetes.io website, you may notice the big portion of information about kubeadm. How can you use it? Why should you use it? And so on. So kubeadm, again, if you are going to deploy Kubernetes cluster on some bare metal machines, we can strongly suggest you at least to start with kubeadm as their first solution. And other solutions include kops, for example. The reason why kops appeared in the market is that it was, for a long time, it was the single and the best solution to run containerized, for run Kubernetes workloads on AWS. So as you definitely know, AWS is the leader in the public cloud space. But unfortunately, until the latest time when they have announced their own service, EKS, there was no way by Amazon to run Kubernetes on top of their machines, on top of their environment. But again, AWS is the most popular solution in the public cloud world. So there have been lots of customers, lots of users who would like to run Kubernetes there. So kops is a solution that is being prepared by the Kubernetes community. It's absolutely open sourced. It's available for anyone. And for a long time, it was the most recommended solution to run your Kubernetes workloads on top of Amazon Cloud. And even today, when EKS has appeared, kops still offers you some extra features compared to EKS, because with kops, you have control of the control plane, for example, if you'd like to have some fine-tuning and so on. So for many cases, even today, kops is the preferred way of running Kubernetes workloads on AWS. And another solution is kubespray. It was also known by Cargo before. So kubespray is a pretty simple solution with really wide capabilities. So the biggest benefit of using kubespray, if I open their webpage and documentation, you may see that they are supporting multiple Linux distributions. And they also support multiple versions of, for example, container runtimes, or of public or private clouds, and so on. So I can open that on GitHub, where they have more detailed information about the project. And here we go. So it can be deployed on almost every kind of public or private cloud that is popular today. It allows you to deploy your cluster in a high available way. It's composable, so you can easily use any networking solution, for example. It supports the most popular Linux distributions, especially the Debian-based and Red Hat-based. And it also contains some CI tests out of the box. So I strongly recommend you to check this project if you are interested in some way how can you deploy customized enough Kubernetes cluster. Why I mentioned that kubespray is pretty easy is that because it's simply a bunch of Ansible playbooks. So if you're familiar with Ansible, you can easily use kubespray and customize it in any way, any kind of like. All right, so this is the main ways of how can you deploy Kubernetes almost everywhere. In real life, we have much more service providers, much more companies that are offering the similar services on-premise or in the public clouds. But here on this slide, the most popular of them are mentioned. All right, so coming back to Minikube, as I mentioned before, it's the community-suggested way how can you run Kubernetes locally on your local machine. It can be even not a local machine, but it's mostly intended for using locally. So it can be run inside a VM on Windows. It can be run on Mac, and it can be also run on Linux. And also there is an extra option with Linux that you should not definitely use a virtual machine on Linux. You can simply, if you have Docker installed on your Linux machine, you can run Minikube without any extra virtual machine. So it will not bring any overhead and overload for you. The major requirements for installing Minikubes, first of all, it's kubectl. kubectl or kubectl, kubectl is the CLI tool for Kubernetes. So if you'd like to control Kubernetes cluster from CLI, you should use kubectl. For macOS, the major requirements are listed here. Minikube for macOS can use HyperKit. It may use HAV driver. It may use VirtualBox or VMware Fusion. For Linux, you may use VirtualBox or KVM, or as I mentioned before, you can use the raw Docker. And for Windows, you can also use VirtualBox or Hyper-V. So as you could notice on this slide, all this installations support VirtualBox, which is a cross-platform solution to run virtual machines. So if you are absolutely newbie to Minikube world and you are fine with using VirtualBox in your environment, please use it. And of course, you should have enabled the hardware virtualization in BIOS, and you require the internet connection on the first run of Minikube because it downloads some assets from the outer world. So on this slide, you may notice how can you install Minikube on your local machine. I'll open this link here. So on the slide, again, you may see kind of pretty complicated line for installing Minikube on Linux. That's just a line that downloads the prepackaged Minikube binary from GitHub, places it into user local bin directory in your machine. You can do almost the same with macOS, but there is also an option available with Brew. And you can also, on Windows, you can also install with Chocolatium. So here on a Minikube repo, you may find this information. I have to also mention that in the Minikube releases section, there's also support for Debian packages. You may see them there, and you can download them right here on GitHub from the releases page. They are currently in an experimental stage. So if you're not ready for experiments, I can suggest you just run the prepackaged binary from here as well. All right. So you can access Minikube again, as you can access any kind of Kubernetes cluster. You can access it with the command line interface with CLI, kubectl, as I mentioned before, you can access this with graphical user interface, with the web dashboard, and directly via APIs. You can run the API calls that will directly interact with the API server on your Kubernetes cluster. So with kubectl, there are lots of ways how can you install it on your machine. Again, the recommended way is, the suggested way is if you're using a Linux machine, so please use the repos that are currently prepared for Debian-based distributions or to Red Hat-based distributions. You can also use Snap on Ubuntu. For macOS, you can use Homebrew together with Mac ports, and you can also install it on Windows machines, also with Chocolatey and some different tools. And if you're using Google Cloud, for example, and you have your workloads, your Kubernetes workloads being provisioned on Google Cloud, there is an alternative where you can simply use the Google Cloud CLI to install kubectl. And of course, there is a way how can you install these binaries directly using curl. If you have installed it, so you can simply check if it works. So on my machine, I have already pre-installed it. I'll make my phone bigger. I hope you can see at least something. Yeah, so just print something like kubectl help, and if you have an output, so you can verify that kubectl is working. Right, so the dashboard is a different way how can you access and how can you interact with Kubernetes cluster. It is bundled into the Minikube installation. If you are, first of all, it's not really the recommended way of managing Kubernetes clusters because it's a bit more unsecure than managing Kubernetes clusters with CLI. But if you're the UI person, you can use this command on Minikube to run something on, to run the dashboard on your Minikube installation to access your Kubernetes cluster. Here's the screenshot of how does it look like. So much more user-friendly than the raw CLI, but again, the pure CLI and the pure API are much more flexible and can give you much more benefits in different cases. So you can also use the kubectl proxy command specifically with Minikube to access your Minikube UI. Right, so let's move on with the Kubernetes objects. What are the major parts and major pieces of Kubernetes? So Kubernetes has the object-oriented model, and all the components and all the pieces of Kubernetes are actually the objects. So these object entities describe what containerized applications we are running and on which node, where exactly we are running them. We can define the application resource consumption, and we can define also different policies for data attached to applications and so on. The most well-known and popular objects include pods, include replica sets, include deployments, namespaces. It's just a brief list, but the real number is much bigger. Here we'll just take a look at some of them that are most actively and widely used. So pods. As I mentioned before, pod is the smallest and is the atomic unit of Kubernetes. And if you're running your applications on Kubernetes, they've been running pods. Pod is actually the virtual unit within the Kubernetes working node, where you may have a single or multiple containers. The biggest difference of pod compared to other Kubernetes objects is that all the pods should be run on all the containers within one pod should be run on exactly the same worker, on exactly the same machine. Containers are sharing the namespace. You can also attach some external storage to them, but you are not directly attaching storage to your containers. You are attaching storage to your pods. Pods are scheduled together on the same host, and so the primary use case for pods is that you may have the multiple versions of the same application bundled into the single space. There is a concept of labels at Kubernetes. So labels are the key value pairs that can be attached for any kind of Kubernetes objects. For example, on this diagram, we have keys app and env, and values for them, respectively, front-end and dev. So you can easily sort or define your environments or different objects within your Kubernetes cluster. So if you're looking for pods that are intended to be used on front-end nodes or for the front-end purpose, you can label them with app front-end for the dev environment. You can also do the same, for example, with backend. And if you are using them in a different environment, not in the developer environment, but in the QA environment, you can also do the same. Just the brief sample, so you can attach any kind of key and any kind of value to your Kubernetes objects. The way how can you use labels is using the label selectors. And one of the reasons, and actually the reason why should you use labels, is that because you have to consume them in somewhere. You can consume them with label selectors. With label selectors, we can select a subset of objects. So for example, if we are looking, as in this diagram, if you are looking for all the environments, for all the pods that are located in the development environment that currently have the value of dev for key env, we can simply select all these two pods that we can see on the top of this diagram. And we will not select two on the bottom because they are not satisfying this requirement of the development environment. There are two main types of the selectors. First of all, these are equality-based selectors where you explicitly mention what kind of objects would you like to retrieve, or you explicitly mention what you don't want to retrieve. In this sample, we see in its environment dev. Or you can also use the set-based selectors that allow you to filter. For example, as here, we may see that we may select multiple we may select multiple pods in environments dev and QA. Another notable concept and another notable object of Kubernetes are the replica sets. So as I mentioned before, for example, if you are running multiple workers with multiple applications that are performing the same function, they can be run on different machines and within different pods. And on this diagram, you can see that we have, so replica set defines the desired replicas number. We would like to have 3 replicas of our application on our environment. The current state is also 3. We have 3 applications that are used, and the current state equals to desired. But in some case, if we have 3 machines, 3 nodes, and one of these machines, for example, goes to reboot accidentally. So in this case, we will have only 2 pods that we have in the Kubernetes environment. In this case, replica sets, as we should satisfy the requirement of the desired replicas, Kubernetes will provision an extra replica on the available resources of your cluster. So the desired state of 3 replicas will be still satisfied. Deployments is a bit more complex way of using replicas of using replicas and pods. So deployments are the declarative updates to pods and replica sets. And actually, in one of their releases of Kubernetes around 1.5 years ago, deployments were presented as the recommended way of maintaining the desired state of your applications on Kubernetes. So deployment controller is a part of the controller manager that we saw on the control plane diagram, and it makes sure that the current state always matches the desired state. So here we can see the deployments. We have the desired number of deployments of 3. We have the specified image of Nginx, for example. In this case, it's 179. And we are asking our replica sets to have 3 replicas of exactly this pod with exactly this image right there. One of the reasons why you should prefer deployments against of their generic replica sets is that actually deployments allow you to perform some more complex tasks like deployment rollouts or rollbacks. So here on this diagram you can see almost the same. We still have 3 replicas of our pod with Nginx, but in replica set A we have Nginx version 1.7.9, but in a replica set version B, we have Nginx version 1.9.1. So if you have the different versions of your applications and you would like to perform the zero downtime rollout of your application to your host, you should use deployments because it will allow you to do it. And another case, again, if you'd like to roll back your application, if your, for example, application version 1.9 doesn't work properly or as you've expected, you can easily roll back to the previous version, and it also can be achieved easily with deployments. Namespaces is actually one of the most important objects at Kubernetes. If you are looking for some kind of multi-tenancy and isolation of the resources. So especially for the cases where you have multiple users and multiple consumers of this Kubernetes cluster, not only you personally, if you'd like to create multiple projects and teams at your Kubernetes clusters, you should definitely use namespaces. The mechanism for them is similar to the Linux namespaces, where you define some area within the Kubernetes cluster that is accessible only for those entities who are allowed to access them. By default, Kubernetes creates 2 default namespaces. It's kubesystem and default. The difference between them is that kubesystem is intended to be used with the Kubernetes native components, with the Kubernetes system components. And default namespace is the default namespace for your usage. So if you do not define any specific namespace for your purposes, Kubernetes will create a default namespace for you. All right, so the next part is about authentication, authorization, and admission control. These pieces of Kubernetes are extremely important if you are looking for some security. So first of all, what's the difference between them and what are the goals? So with authentication, you log in as a user. Authorization authorizes the API requests added by the logged in user. So API server clarifies these API requests as, yes, they are allowed to come here and they are able to be performed here. And admission control also checks some extra policies on your Kubernetes cluster. For example, you may say the quota for consuming your resources, and admission control will check that as well. For example, if you would like your application not to use more than 512 megabytes of RAM, quota can be set, and admission control will enforce using of this quota. So with the basics of authentication. So Kubernetes has two kinds of users. They are not actually users in the common meaning, as we, for example, have in Linux or your desktops. But there are the normal users, the regular users that are using the Kubernetes cluster that are able to perform some operations, and the service accounts. The normal users can be managed by the Kubernetes cluster itself, or they can be managed by some third-party solutions, for example, with the user client certificates, with the files that are listing usernames and passwords, with Google SSO accounts, and so on. The service accounts are the users' accounts that are intended only for performing some specific operations within the Kubernetes cluster. You, as an end user, you don't have a direct control of them. So if you are performing some operation on Kubernetes cluster, you're acting as a normal user. Service accounts are being used by different Kubernetes services. And they are actually created automatically by Kubernetes itself via the API server. Authorization is the next step. So after the successful authentication, users can send the API request to perform different operations, and API server authorize them to perform these operations. There can be multiple authorization models. Here they are briefly described. With the node authorizer is the default one within Kubernetes. There is also the attribute-based access control authorizer that is also known as ABAC, webhook authorizer, that is mostly intended for using with the third-party services, and role-based access control RBAC authorizer. With the latest Kubernetes releases, starting from the version 1.6, the actual version of Kubernetes is 1.11, by the way. So with starting from the version 1.6, using RBAC, the role-based access control authorizer, is the recommended way, because in this case, if you're using RBAC, it will be much easier for you to separate the roles of your users that access in the Kubernetes cluster, to separate the responsibilities there, and so on. And admission control, as I mentioned before, it's used to specify some granular access using the specific policies. And they come into effect after the phase of authentication and authorization being passed. So let's move forward with services. So why we need services at Kubernetes? So first of all, pods. We have pods, right? So I mentioned before that pods are the atomic unit of the Kubernetes cluster. But you, as an end user, you don't interact with pods directly. And of course, you don't interact with containers directly. You have to interact with some more high-level abstraction. And service is exactly that high-level abstraction that allows you to manage your applications. Pods are ephemeral. So any pod with containers can be destroyed at any point of time, even if you have your worker node rebooted, for example. The specific pods will be destroyed, and other pods will be provisioned on a different machine. And as I mentioned before, pods are sharing the same networking namespace, and they also have the unique IP addresses. So if your pod will be destroyed and the new one will be provisioned, it will be provisioned with the new IP address that is only known well, it's not only known to Kubernetes cluster, but Kubernetes cluster is the best person to interact with this IP address, not you as an end user. You as an end user, you require some more high-level abstraction to interact with something that is being run on your Kubernetes cluster. So service is the logical group of pods, and services add a policy to access these pods. So you, as the cluster operator, you interact with services. You don't interact with pods. Here on this diagram, you can see how we have multiple services. For example, we have front-end and database that are using pods on the right side of the diagram. So again, we have different label selectors here. First of all, we have an operator. We have a user that interacts with them. We have the label definition front end. We have the label definition database that have the virtual IPs that are different, that are specifically dedicated to these services. And these services are interacting with pods that are deployed, let's say, in a Kubernetes backend. So if, for example, this application front end with IP address 10.01.05 will be destroyed, the new pod will be provisioned with the same IP address, but ending with 6, for example. And only servers will be aware of the new IP address. If you'd like to access this pod directly, you have to go and write some commands at command line to retrieve the actual new address of your pod, and that's definitely not the best operational experience. So, as an end user, you should interact with services. Another important part of the worker nodes is kubeproxy. So, as I mentioned before, kubeproxy is a daemon that is a networking component that interacts with the API server, and it performs operations of addition or removal services and endpoints on the worker nodes. And kubeproxy, it also manages the IP tables roles on the nodes, and when the service is removed, it also removes the IP tables roles there. Here in this diagram, you can see how API server is interacting with kubeproxy. So we have multiple worker nodes which have multiple applications deployed on them with multiple IP addresses, and and specifically here we can see how the worker node 2 using the front end service interacts with worker node 1 with the pods that are deployed there. Another object within Kubernetes is the service type. So when we are defining the service, we can also choose its access scope. We can decide if the service should be accessible only within the cluster, it should be accessible, or it should be accessible from within the cluster or the external world, if you'd like to access these services from the external world. And it can be also mapped to the external entity which is residing outside of the cluster. So this use case is common for the cases when you, for example, use a Kubernetes cluster for running only stateless workloads, but you use some stateful database that is deployed outside of Kubernetes. And the access scope is defined by the service type. The service types, the well-known service types are cluster IP and node port. So cluster IP is the default service type. If you're deploying the servers, like the default service type that will be assigned here is the cluster IP. Every service in this case gets its virtual IP using the cluster API, and this IP address is used for communicating within the service and accessible within the cluster. So this is being done for the security purposes. Another type of service types are the node ports. They are useful when we would like to make our services accessible from the outer world, when you'd like to have your application accessible from your web browser on your machine, for example. So here on this diagram, you can also see how these interactions are happening. So with API server, we have kubeproxies deployed on the nodes, and we also have the front-end service that is interacting with the worker nodes. And here on these nodes, you may notice the ports that they are using. So another service type is load balancer. Load balancer is widely used for environments that explicitly support it. For example, the Google Cloud Platform and AWS. If you are running a Kubernetes cluster on Google Cloud environment, the easiest way to have an external access, from the outside world to your Kubernetes cluster is to use the load balancer. So it's pretty easy. When you are deploying the new services, they are automatically created, and the external load balancer that is natively compatible with Kubernetes will route to them. So, for example, with the Google Cloud Platform approach, then the Google Cloud Platform load balancer is being used, and it routes your direction to Kubernetes cluster. And here on this diagram, we can actually see that. Another great sample and the most well-known sample of how can you reach your Kubernetes cluster from the outer world if you are not using Google Cloud, if you are not using AWS, is using external AP. So a service can be mapped to an external IP address, so it could be routed to one or a few worker nodes. The downside well, it's not a downside. So in this case, traffic is ingressed into the cluster with an external API for the server's port. Yeah. So now we can run a brief demo of deploying the standalone application. So on this link, it's in my GitHub, github.com/Dvoretskyi. Intro to Kubernetes, you may find the web server YAML, where we explicitly define that we would like to deploy we would like to have deployment. I'll make it bigger. So we'd like to have deployment. We're calling it web server. It should use the label of application Nginx. We'd like to have 3 replicas. Again, it should use image of Nginx and Alpine, and it should be available on port 80 in the default the default port for that. So as I mentioned before, I have the Minikube cluster already provisioned on my machine, and we can easily, oops. Yeah, it's easier to do from here. So we can simply create the new web server deployment. Okay. Okay, so it already exists. I have created it previously, so it simplifies our life a lot. So here we can check which kind of replica sets we currently have. And here you may see that we have replica sets with web server. We have 3 desired of them. All of them are ready and available to use. Again, using kubectl, we can create the service, and the service definition in a YAML file is also available here. We're also using the name web service. It specifies the type of node port. It should be available on port 80, uses the protocol TCP, and it uses the app Nginx. So again, I've created it previously. We don't have enough time to redeploy that, so I'm just checking what do we have here. Here we have all the services that are available in the cluster. So here's the Kubernetes servers that is the default one that's been deployed by Kubernetes itself when we created the cluster. And here we may see the service that is called web service with the specified cluster API, which is available only within the cluster itself. And we have this application available on port 80 that is publicly routed to port 32742. And we can actually get more details about the service with the describe command. So describe command of kubectl is the easiest way to receive like really detailed information about what do you have currently within your Kubernetes cluster, and what is the specific setup of your services. And we can test this app actually. So one of the benefits of using Minikube is that there is a way to easily retrieve the IP address of the service, and it's here. So here's our IP address of our Nginx installation. And we can simply use curl to see that we are using Nginx. Pretty easy. Right. Unfortunately, we are running out of time, but I have also a few notes about the Kubernetes community. So everything that I presented before was the real basics of Kubernetes, Kubernetes itself, of Kubernetes as a technical project. You can definitely use the Kubernetes documentation to dive deeper into that, but if you're also interested in diving deeper into Kubernetes as an open source community, there are multiple ways of how can you get started with that. So first of all, we have the weekly regular meetings. The biggest meeting, the most popular meeting with the biggest number of attendees is happening every Thursday at 10 a.m. Pacific time. We have multiple and various meetup groups across the whole globe. We have more than 1,500 official CNCF meetup groups. We have Slack channels that are Kubernetes alternative, Kubernetes community alternative to IRC channels that are also popular in the different open source communities. We have mailing lists, for example, Kubernetes Dev, Kubernetes-Dev is one of the most popular mailing lists within the community where you can ask your questions specifically regarding the Kubernetes development. We have lots of special interest groups within the Kubernetes community. So if you're looking to solve specific problem or question within the Kubernetes, you should reach out to one of these special interest groups. And definitely Stack Overflow with Stack Kubernetes. You can find lots of useful information about some existing issues that could have happened with different users, or you can ask your own, of course. And I have to mention that CNCF is also organizing the big worldwide events comparable to the scale with OpenSource Summit that is happening here. So we're organizing the KubeCon, Cloud Native Con in Europe, in China, and in North America. And two next editions that are coming later this year. We have the Chinese event that will happen in November in Shanghai, and North American one that will happen in Seattle. So what can you do next after we just reviewed Kubernetes really briefly? You can apply for passing a few courses by the Linux Foundation. It can be the self-paced Kubernetes fundamentals course that will be much more complicated than that one that I showed you today. And we also have the instructor-led Kubernetes administrator course. And you can also apply for certification with the CKA exam, it's Certified Kubernetes Administrator exam, or and a Certified Kubernetes Application Developer program that is mostly intended for people who are developing applications to be run on top of Kubernetes. So CKA exam is mostly for operators and administrators. CKAD is mostly for people who are developing something to be run on top of Kubernetes. And that's all from me. We have a few minutes for questions. You can actually reach out to me on Twitter, on GitHub here, and Kubernetes.io is the official website of Kubernetes, and CNCF.io is the official website of CNCF.
The load balancer, does it run on the master node, or where does that run?
So load balancer is the virtual entity of Kubernetes. And if you are, so load balancer is under the hood is the servers. And services are like the high-level abstraction on top of pods.